There you go. All right, I think it's recording now. Let me check. Yes. All right. So we were talking about impact, right? I started talking about that in videos in last week, right? And I generally told you that impact actually is something that we deal with uh, quite often in engineering analysis. I gave you a couple of examples. I won't go over the slides again. I talked about conservation of linear moment and impacts, right? Basically, when two objects hit each other in a very simple form. So we have total linear momentum of these two objects is conserved, right? But along the line of impact. Now, I said when we have an impact, there are two possible outcomes. One possible outcome is that these two objects hit or collide, or to say technical term, and they just stick together after the impact. Right? That's one possibility, depending on what kind of material those are made of and the way they hit each other. If that's the case, then we are going to have one object, right, after the impact. Like before impact we have two, after the impact we have one, and the one object or one particle or one rigid body is just going to be moving with some velocity. And remember, this is part of momentum methods, and generally speaking, when we were dealing with, or we've been talking about, when we talk about energy methods and momentum methods, we're mainly focused on velocities. Remember, we said focus on force, time, position, and velocity. And that's our main focus, as opposed to um, Newton's method that we were so focused on acceleration. Here we're more focused on velocity in terms of parameters related to kinematics of an object. Right. So if you know velocities before the impact, right, only one equation, you just get the velocity of the final object or the object that or the particle that is formed because of that impact. You can get the velocity of that, right? And we used basically principle of linear impulse and momentum to find this velocity. We said, well, the total linear momentum of these two objects are the total is conserved, so we can find the final velocity. Now the second possible outcome is that if they don't uh, adhere to each other, if they don't stay together, right? We have relatively hard objects, let's say, they hit each other and then they you know travel apart or just move away from each other. Now, in order to make our life a lot easier, we I started basically classifying the type of two types or two cases. I only talked about case one, and that's the case when these two objects, well, we're still part of possible outcome two. These two objects do not stick together after the collision. But case one was direct central impact, meaning when these two objects or these two rigid bodies or these two particles, they both travel along the same straight line. Right? Travel along the same straight line, they hit and they travel away. Now, pay attention to the drawing here for these two particles on the right. I put before impact, during impact, after impact. See that I took, again, just want to emphasize, when we talk about momentum methods as opposed to energy methods, in momentum methods we care about the directionality of vectors. We care about the directions. We care about, that means I had to put this here just to emphasize these are vectors. Right? So we have magnitude and direction. So we care about direction. So we have to take one direction as positive, right? In direct central impact. In this case, I took direction towards right as positive. You can think about it as x or just some positive direction, right, along this straight line. And I said, well, at the beginning they both are moving to right, so positive. A is going faster than B, so it hits B from back, and then both keep going to the right after the impact. Right. In this case, assuming that the velocities are positive before and after the impact, these are the relationships we get. All right, this is the first relationship, this one and this one. And we said the first one, well, it gives a relationship between velocities before and after impact. It's one equation, two unknowns. We need a second equation. The second equation comes from the idea of coefficient of restitution. What is that? If you remember, I briefly explained that. It's basically something we calculate experimentally, right? And the idea is that as a result of this impact, part of the object's kinetic energy can be lost, right? There's an impact. That loss of energy can represent itself as deformation when a car hit a wall, right? So part of the energy is used to or part of the energy causes some dent in a car. It can be released, part of the energy, as a sound, right? When there's an impact, depending on the materials and how hard the materials are or what they're made of, those objects, you might hear some sound. Accident has a sound, as you hear that. Right? So these are the types of, remember, energy is conserved generally, but it basically transforms from one type to another, right? So in this case, the kinetic energy is transformed from, well, kinetic energy to other type of energy that is used to deform the object, create sound, create heat, depending on what situation you're in. So that's the idea of coefficient of restitution. It tells us how much of this kinetic energy is lost during the impact, right? By looking at velocities before and after. Now, this E, as I said before, depends on properties of the object, the velocities, the orientations when they collide. So we basically find this E experimentally for different materials. Now, based on this E, you can classify the impact. You can say if E is 0, right, so no energy is lost, right? Let's put it this way: if E is 0, right, you have a perfectly plastic impact, and if E is 1, right, you have a perfectly elastic impact, meaning that whatever are the velocities before, the energy you have before and energy you have after, they are the same. Nothing is lost if E is 1. Right? But typically, for typical impacts, we are somewhere in between. All right, so that was direct central impact. It's a long introduction, just to refresh your mind, hopefully. And then the second case would be, well, we go a little deeper and we'll say, well, what if this impact is not a direct central impact? What if these two objects collide with some angle? Right? Which, again, it's not that uncommon. Right? So we went over a couple of examples. I won't go over these. I just want to go over and go to the second case. Case 2. Let me use the same color. So case 2 would be oblique central impact. All right. In this case, you can think about, let's say we have A, right? And this is B. Two objects, two particles. Let's say A is moving in this direction with VA, and B is moving in this direction with VB, velocity. If you follow that, they get to some point, and there is going to be an impact. I can do a better job probably there. No guaranteed, but I can try. So that and that, this is A and this is B. And then after they hit, they just travel away. They move away from each other. Right? That would be like this goes this way, this goes this way. This is a general form that. And then if that happens, I'll try to do a better job there. If that happens, then you'll have A here with some velocity after the impact, and you have B here with some velocity after the impact. That would be oblique central impact, meaning that these two are not on the same straight line, right? They just come, hit, and they just, let's write it this way. objects A and B approach each other with some velocities, obviously, VA and VB. All right, get together, and then there is a collision, and then you just travel away. Now, we have to define two things. The way we deal with this kind of central impact is that the force, let's think about it this way, the forces they exert on each other, right, during the impact, these forces are parallel to some line. So if they come like this and they go like this, the impact that happens, the force they exert, like A applies to B and B applies to A, they are on a line. I think that's the line of action, line of impact, we call it. So we can draw it like this. This would be, you can look at it as XY axis. This would be X, this would be Y. X is basically, let me write it here. This is line of impact, and this is plane of contact. Plane of contact. That's why. There's a plane of contact where this contact happens, right, along the surface of these two objects hitting each other. And then there's line of impact. Right? You can just think about them as X and Y. So the forces they exert on each other during this impact are parallel to X-axis. Right? And it's all these are just objects, but if you think about them as rigid bodies with some center of mass, these forces are pointed towards their center of mass. Now, what happens is that along the line of impact, right, similar to what we had for a direct central impact, right, along this line, we have the momentum of the system, right, is conserved, and we also have a coefficient of restitution. Right, in this, you can think about the X axis or line of impact as just similar to direct central impact. Right? So what we care about is the X component of velocities. What I'm trying to say is that, you can write it this way, in X direction, right? Let's put it this way, moment of the system is conserved. I don't know what did I write right there. In X direction or the line of impact, along the line of impact, moment of the system is conserved. All right. That means that MA, VA, now VAX, the X component of velocity. I only care about what's happening along the line of impact or X-axis. Right? Plus MB, VBX is equal to MA, VAX, or VA prime X plus MB, then we have MB times VB prime X, right? Prime being the velocity after the impact. So remember, these are vectors, right? This is a vector. It has X and Y components. This one is a vector. Okay. So this is in X direction. Again, you can think about along the line of impact or X direction as a typical direct central impact. All right, the moment of the system is conserved. Now, this is one equation, two unknowns. Obviously, you can also add the whole idea of a coefficient of restitution that basically relates the velocities along the line of impact. All right, so you also have E as a coefficient of restitution, VB prime X minus VA prime X, right? Velocity in, if I can, E is equal to over VA, what's this direction, X, right? Velocity of X, of A before impact, minus velocity of B before impact. So these two equations, similar to what we had for direct central impact, these two equations are enough to find two unknowns. Remember, you are trying to find the velocities. That was the whole story of impact. We said we know, this is general question is, if we know the velocities before impact, what would be the velocities after the impact? Because knowing that also gives us an idea about how much energy is lost, or how much of the kinetic energy is still there, right? These two equations, very similar to what we had for direct central impact. The only difference is that now we just look at the X component of this oblique central impact and treat that as a direct central impact. So you have two equations there. Right. Draw this one, and this one. Probably made it uglier than before, but having these two equations, you find the X component of velocities after the impact, right? VA prime X, VB prime X. You have now two equations, two unknowns, assuming that you know E, coefficient of restitution, which experimentally can be calculated and you're given. So from these two, you can actually find, right? You can find VA prime X and VB prime X. Right? So you can find these two equations, two unknowns. No vectors. All right. So this is in X direction, or along the line of impact. Now, in order to know the velocities after the impact, obviously you also need to know the Y component of velocities. Now, the good news is in Y direction, and if you're in three-dimensional space, even in Z direction, let's just stick to two-dimensional space, but the story is the same. In Y and Z direction, the moment for each particle, the moment is conserved. So in Y direction, whatever its moment before the impact is the same as its moment after the impact. Same story for particle B. Whatever is its moment before the impact is the same as its moment after the impact. So each particle, you can think about this, a moment of each particle is conserved along Y-axis or Z-axis coming out of the screen. Right? If this is X and Y, you get your Z-axis in the center somewhere here. Let me just not make it crowded there. Z coming out of the screen. Right? So I can write it this way. In Y direction, let's write it as moment of particle A is conserved only in Y. No, conserved along, let's put it this way. Conserved along Y-axis. And this particle A, you can write it as particle B. They're just the same story. And y direction, you can write it as z direction. Right? There is no impact. Think about it this way. There is no impact happening along these two axes. We only care about line of, well, not that we only care about, but impact is only happening along the line of impact and perpendicular to plane of contact. So you form two, you put two axes. One is line of impact along the impact. One is perpendicular to that line of impact, which is plane of contact. You find one, you'll find the other one. Right? They're perpendicular with respect to each other. So if that happens, that means the velocities in y-axis and z-axis don't change for these particles, y components of velocity. So what I'm trying to say is that, for instance, we get VA prime y is equal to VA y. Well, the general form would be MVA prime y is equal to MVA y. Right? The mass is there too, because before and after M, but you can just cancel out the mass. All right, it's the same particles. MA VA prime in y direction is equal to MA VA in y direction. And the same story for z. You can also write it for A as VA prime z is equal to VA z. Right. Nothing is happening along those. No impact is happening. So, and you can write it for B. VB prime y is equal to VB y, and VB prime z is equal to VB z. This is supposed to be V. So now you can calculate the velocities after the impact. Right? When this oblique central impact happens, if you know the velocities before the impact, well, obviously you need to know the components of velocity before the impact along x and y. Right? Then you can find the components of velocities along each axis after the impact. Right? From the first two equations, you find the components of velocity along x-axis or line of impact after the impact, and following the whole idea that the moment of each particle is conserved along y-axis and z-axis. Obviously, this should have the z-axis. You can find the component of velocity after the impact. All right. And knowing that, knowing x and y components, you have the velocity after the impact. All right. Now, let's. There's one special case. If, well, it's not very special. It's just, well, I guess we can call it a special case. When we hit, when one of these objects is just a fixed rigid body or object or particle. When does that happen? Let's say you threw a ball towards a wall, right? Some fixed object. A good example would be the wall. You threw a basketball to the wall and it just hits the wall and it bounces back. Right? So in that case, you can think about B, particle B, being just a wall. It's fixed. There is no previous velocity. There is no velocity after the impact. There is no velocity before the impact. Right? It's just staying there. It's a fixed object, fixed surface. Your only object or particle is A. So that would be the special case for this. If you put velocity of B in x direction before and after the impact 0, right? That'll give you the relationship between the velocities before and after the impact for that object you're throwing towards that fixed object, no, that gives you that relationship. Let me write it. It's probably better to, instead of saying that. Special case, right? When object, let's say object A has better to say, let's put it this way. Object A hits a stationary object B. All right, this is what I'm talking about here. So if these are still the line of impact and the plane of contact, or XY components, X and Y. Now what happens is that you have A going there, maybe VA. It goes there, it hits this part, and then bounces back. Then you have your A, and this is VA. B is just some fixed place. It's like this is B. It's just some fixed wall, fixed stationary object, something that is not moving, put it this way, permanently or temporarily. Then in that case, you just use the relationship for E. Wherever you have the relationship between velocities, we can just put the velocity for B as 0, right? Before and after the impact. So if I want to write, let's say, coefficient of restitution, that would be VB prime X minus VA prime X divided by then VA X minus VB X. Now in that case, since B is not moving, this is 0 and this is also 0. So I can get a relationship between coefficient of this restitution and the velocity of A before and after the impact. I'll get VA prime X is equal to that. If I did everything correctly, it should be VA X, so minus, there you go. So that becomes the relationship. So if, again, special case, meaning that just pay attention that hitting one object, hitting the other object, it doesn't have, both objects don't have to be moving. One can be a stationary. All you have to do is that put velocities as 0. All right. That's pretty much all about oblique central impact. We're going to go over a couple of examples and see how things work. I'll go over, I guess, one today, and I'll go over 1 or 2 in next class. We'll see how things go. But so that's the general idea. All right, things change from a direct central impact to oblique central impact. The oblique central impact situation is that, well, you always have to find the line of impact and plane of contact. One of them, the other one is perpendicular to that. And along the line of impact, or x-axis as we call it here, you get two equations similar to central impact, similar to direct central impact. And in y and z other axes, there is this whole idea of that the moment of the particles is conserved, and there is no impact. No impact is happening in those along those axes. So velocities, components of velocities in those directions are going to stay the same before and after the impact. And the special case is there too. All right, let's take a look at an example. That's not what's supposed to happen. All right. Let's go with something very straightforward first. Now, let's go with this. We have just basically two big objects hitting each other. Let's, well, that's the story of the whole topic. But let's say this is A, and then this is B. They're not supposed to go inside each other, but that's as good as I can draw them. This is A and B. Then let's say this is the line of impact. This is the plane of contact. Let's just call this X and Y. And the problem statement goes as the 3 kilogram object A and 8 kilogram object B undergo an oblique central impact, well, that's the only kind of impact we know. So even if you're not told that it's oblique central impact, we don't really talk about any oblique non-central impact. So just, you know, the coefficient of restitution is equal to 0.75. Oh, I don't know where they get 0.75. It's 0.8. Before the impact, right, VA is 10I plus 4J plus 8K meter per second, and VB is minus 2I plus 6, well, minus 6J, minus 6J plus 5K meter per second. And the question is, what are the velocities of A and B after the impact? All right. So this is a relatively straightforward problem. We are given velocities as vectors, ijk components. In so many cases, you actually end up finding the components along x and y axis, knowing the magnitude and the angle it creates. We'll get there. We'll go over an example about that one. So we only care, not we only care, the impact happens along the line of impact, or x-axis. All right. So the components of velocities, let's put it this way, we established that the components of velocities along plane of contact, right, in y and z axis, they don't change before and after the impact, right? So by looking at this, you realize that, well, if the velocity of A, the y component of A is 4 meter per second, and z component is 8 meter per second, well, these components are going to be the same after the impact, because the line of impact, the way we are given these in x, y, z coordinates, is x is the line of impact. So this is a line of impact. Line of impact, right? So we only care about the x component. Or better to say, we have to calculate the x component. That's the direction. That's the direction that the impact is happening. Right? So knowing the coefficient of restitution and velocities, x component of velocity for A and B before the impact, we want to find the x components of velocities for A and B after the impact. All right? So let's write in this direction. In x direction, you'll say MA VA X plus MB VBX is equal to MA VA X prime plus MB VBX VB prime X. Oh, let me just put the primes inside. That's what I've been doing. Stick to the same notation. All right. Here we know MA and B, we know VA X and VBX, like MA is 3 kilograms, NB is 8 kilograms, VA, X component of VA is 10, X component of B is -2. This is 3, this is also 8. So we get the relationship from this, we get one equation, right? Equation 1, you can think about that. So the relationship between VA prime X and VB prime X. One equation, two unknowns. We need another equation that would that one comes from the coefficient of restitution, right? So the second one would be E is equal to, right, VB prime X minus VA prime X divided by VAX minus VBX. If you want to put this in Word, I don't know, maybe it makes more sense to some of you guys. If it doesn't, just stick to the equation. But basically, this is trying to say the relative velocity after the impact over the relative velocity before the impact. I guess the general, if you want to like say it instead of equations and parameters, that's what this E is trying to tell you. It says relative velocity after the impact divided by relative velocity before the impact. Right. But if it makes less sense, don't worry about it. Just stick to the formula there. E we know is 0.8, right? VB prime, well, we don't know that, right? That's what something we want to find. VA prime, we also don't know that in X direction. These are the velocities after the impact that we're looking for them. Then we have 10 minus -2. So from this one we get VB prime X minus VA prime X is equal to 12 times 0.8. Let me see what they get there. I got 9.6. So 9.6 meter per second. This is the second equation. All right. So now we have two equations, two unknowns. How you can solve this? Mathematically speaking, should be good to go. If you do that, I'll write it this way. 1 and 2 will give you VA prime X is equal to, and VB prime X is equal to. So I'll give you VA prime X turns out to be minus 5.71 meter per second, and VB prime X turns out to be 3.89. Hopefully I can read my handwriting correctly. These are the X components of the velocities for these objects after the impact. All right. We basically used these two equations. We found X components. Now for Y components and Z components, well, let's just stick here. They are the same before and after the impact. So no calculation is needed. All right, here is what I'm talking about. These are the same. And for both particles after the impact, they are the same. So if what I'm asked to find is the velocities of A and B, all right? So I know VA, the X component of velocities after the impact, all right? And I know Y and Z components of velocities after the impact because they are the same. So I can write, so velocities after the impact will be VA, well, I guess prime is, well, I know the X components minus 5.71 Y and Z components are the same. So that would be 4J plus 8 k. For B, VB prime, we'll get, well, we got the x components, 3.89 I. J and K are going to be the same, those components along Y and Z axis. So minus J plus 5K. So this is what we were looking for. These are velocities after the impact. All right. So relatively straightforward, this problem. Now you might ask, so where is the problem? Right? When do we have so in a more complicated case, or more advanced case, or more, not even advanced, something that you typically face is that you're not usually given the velocities like nicely with ijk components or components along x, y, z, or x, y. Typically we solve problem in two-dimensional space. You are given the velocity as with some magnitude and some angle. So you have, what you have is the same. These equations, the set of equations don't change. But the unknowns might be sometimes tricky to identify, or writing the equation might not be as straightforward as this. All right. We'll do an example on that for the next example. Any question on this one before I move on? So your goal when you're dealing with an oblique central impact is that you are tasked in so many cases, you actually have to find out this line of impact. This is pretty straightforward. Line of impact is there. The velocities are identified with their components. In some cases, or in a good number of cases, you have to identify the line of impact and the plane of contact. They're perpendicular. You find one, you can find the other one. And then find the components of velocities along those axes. Right? That's usually what you do with deal with these problems. I'll give you the next example, at least the problem statement, then I'll stop and we do the quiz, and I'll continue that example in next class. I'll finish in next class. All right, so that's an example of those kind of cases, plus the special case we had. So let's see if I can put it together. So we have a surface, inclined surface like this. It creates an angle theta and is fixed. There's some fixed surface. Try to represent it as fixed. Then we have a ball dropping like this way with some velocity perfectly vertical downward, 10 meters per second. It hits this surface, it comes here, it hits the surface right there, and then it bounces back. Not back pretty much, it bounces in this direction. And this angle is alpha. Let me make some room here by moving this to other side. V1 is 10 meters per second. All right. This should be perfectly vertical, this falling down. So let me put the problem statement. The ball A is, well, the ball A of mass M equal to 0.2 kilograms is dropped on a rigid surface, inclined, I don't know what did I write there, inclined at theta equal to 30 degrees. I don't know if grammatically makes sense, to the horizontal, inclined at theta equals to 30 degrees to the horizontal surface. Well, you get the idea. Now it says the coefficient of restitution for the impact move it here, I can see messages. Impact is 0.8, and the friction between the ball and the surface is negligible. So determine one, or A, we have to find the rebound speed V2 and the rebound angle alpha. Part B, the percentage of kinetic energy lost during the impact. All right. So now you see the it's not as straightforward as before, right? It's, you're not given the velocities exactly with their components. You are given a velocity V1 as 10 meters per second, the velocity before impact, and you know where the plane of contact is, right? This is the special case, right? One object is moving, the other one is just a stationary surface. You can think about this as, if you actually look at this, this is your plane of contact, right? Called Y. Perpendicular to that is line of impact. This line. This is going to be your line of impact. X. And these two are perpendicular. Now, what is your task? Your task is to, given this velocity, right, before impact, your task is to find the components of velocity, right, before impact and after impact. Write the relationship along the line of impact or x-axis, and also use the relationship along the plane of contact or y-axis, right, the equations you got, and figure out, this is generally the idea, how can you use those, how can you leverage those to find these two unknowns that you're looking for. You're looking for V2 and alpha. Alpha is not given to you. And also the components are not given to you directly. You have to decompose the vector, velocity vector along the axis and just find those. And then the second part, percentage of kinetic energy, we'll look into is basically the difference between kinetic energy before and after. Right? You can find that by writing the kinetic energy equation for kinetic energy, or finding the kinetic energy difference, how much energy is lost. Knowing the velocity before, knowing the velocity after, we can find the kinetic energy before and after. You can find the change in kinetic energy during the impact, and you can find how much you lost energy with well, knowing that, and how much is the kinetic energy at the beginning before the impact, knowing the velocity, you can find that, and you can find how much the energy is lost. We'll talk about it in the next class. We'll finish the example. Maybe I'll go over another example about oblique impact. All right, let me just stop here.